Okay, so this is the upward oriented unit normal vector. Yep. Okay. To get the downward one, you just simply switch the sign. So it is, we'll just go right to this one. G sub x, G sub y, and then that becomes a negative 1. So we flipped all the signs over the square root of G sub x squared plus G sub y squared plus 1. Okay? So that is simply how to find a unit normal vector to our surface. If those exist all over the place, then it is orientable. Yes?
How could you have one and not the other if it's just negative?
Okay, now the next set of equations is how to find the normal vectors. So this is the upward one. And remember, this was the downward one. Okay? This would be if you were given the surface parametrically. Okay? So n positive is just r sub u cross r sub v over the magnitude of r sub u cross r sub v. So hopefully you recognize these from our prior things. And if you want the n downward, this one was upward. If you want anyone have any idea how you'll do it downward? How do you switch the sign of a cross product? You switch the order, exactly. So it's r sub v cross r sub u over. You don't have to switch them on the bottom. I don't think it'll matter, but we'll just stick with switching them. It's the magnitude. Okay, and that's going to be downward. Okay, so not a big deal. That's how you find unit vectors. All right, so now we're going to get into our equation for a flux integral. Okay? In general, we will write the flux integral of a surface as the sum of the force of the fluid. So that is the velocity that the fluid is traveling through a region. Okay? We want to add up all the unit normal vectors. So what we're taking is the velocity of the fluid in the perpendicular direction to the surface. That's why we're using unit normal vectors. Okay? And then we're going to multiply that by all of the surface area over that field. Okay? So what you're doing in this is finding you a volume. Think about the velocity of the fluid as also kind of as the amount of fluid that's traveling through. Multiply that by just a normal vector. That just catches the stuff that is going in the direction of the path. And then when you multiply by surface area, you get basically a density times well, not a density. You get a function times an area, and that gives you volume. Think of this like the height, kind of like a height. Okay? Now, to evaluate a flux integral, we need to take it from the surface and change it to the area of the region on the plane. So we've been doing this a lot. So now, to evaluate this, you're going to change that surface to the region in the xy plane of f dot. Okay. Thank you. It is positive. I'm sorry. I'm going to have to remember that. Okay? But then you're going to, okay, so maybe you shouldn't write this down, but you should so that you understand what the heck you're doing. F is a force field. It represents the velocity of the fluid traveling through this field. Okay? What is this here? That's a normal vector. Now we're no longer talking about S. What are we talking about? We want dA. So now we got to multiply by the area. And the area is simply g sub x squared plus g sub y squared plus 1. And then dA. Okay? Now what is this thing down here? It's the same as that. So these cancel. And so what you really are left with is the area over the region of f dot the partial derivative with respect to x, partial derivative with respect to y, positive 1, dA. This is upward. Okay? This one is downward. And I'm sure you're thinking, how are we going to know the difference? You're going to be asked for it specifically. So, in the next example, I'll read it to you as you guys are copying those down. Let S be the portion of the paraboloid z equals 4 minus x squared minus y squared lying above the xy plane. Oriented by an upward normal vector, as shown, a fluid of constant density ρ is flowing through the surface according to the vector field x, y, z. Find the rate of mass flow through S. So, this is our surface. Hopefully you remember what a paraboloid looks like. This particular paraboloid is going to have a radius of 2, and it's going to have a z-intercept of 4. Okay? We've got upward flow. So, and our capital F is x, y, z. Okay? So, what is f sub x? Negative 2x. And f sub y? Okay? So, we are going to integrate. Are you feeling the polars on this one? Got to happen. R goes from 0 to 2. Theta goes 0 to 2 pi. We want F, so x, y, z. If you're thinking, hold on, I thought we were doing polars. We will. We're going to switch to polars when it's convenient, okay? What are we going to dot that thing with? Positive 2x, because it's the negative partial, because it wants it upward. It's stated in the directions, the upward one, and that's why I've got these arrows pointed like this, okay? Otherwise, you wouldn't know. So it's going to tell you whether it wants the upward or the downward, because it'll have an effect. Okay? So 2x, 2y, positive 1. And then we can't forget our R. And our R is going to multiply by this entire thing. What is the answer to a dot product? Is it a scalar or a vector? It's a scalar. So 0 to 2 pi, 0 to 2. What is our dot product here? Okay? Well, integral from 0 to 2 pi, integral from 0 to 2, of 2 times what? R squared. What does Z equal?
4 minus R squared minus 1.
So isn't that just 4 minus R squared? Right? I don't think there should be a plus. Oh, yes, there should be. Yes, 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 yes. Plus. And then this whole thing times R dr d theta. Okay? What do you get on the inside of that bracket? You get 4 plus R squared, or R squared plus 4. So when you multiply that by R, you're going to get R cubed plus 4R dr d theta, which is equal to the integral from 0 to 2 pi of R to the 4th over 4 plus 2R squared from 0 to 2 d theta, which is equal to of 12. We're going to put the row in at the end to thank you, okay? And so you end up getting 24 pi. Now that's just the volume. So if they were asking you for the volume, you would say that there were 24 pi units cubed per second. It's a rate. 24 pi units cubed per second of fluid going through, but they didn't want the volume. What do they want? They wanted the mass, so this is just a little, you're just going to add that factor of rho, because they told you the density of it was rho. And now we are in mass, sorry, not equals, mass units per second. So that's the amount of fluid traveling through per second through this shape. Okay? And that is hard stuff. I'm going to pause the video and answer your question. Boom!